trying to recognize any names. So I think we will not delay any further so that the speakers can maximize their time for the presentation and we can have the discussion at the end. So I would like to welcome and introduce our four panelists. For kicking us off today will be my colleague and co-founder of the Women in SVC Committee, Lara Maroto-Diaz. She will be sharing her journey so far into the world of PVD. Lara holds a bachelor's degree in telecommunications engineering and completed her master's degree in biomedical engineering at the Public University of Navarra in Spain. Lara joined Gencoa in 2020 as an R&D technologist, but has just recently advanced into the technical sales role. Next, we will have Dr. Anna Victoria Oniszczuk talking all things HIPIMS. Anna is a vacuum process specialist in Truff Hüttinger with over 10 years experience working with the technology. Anna holds 2 master's degrees in theoretical and applied physics and earned her PhD in 2016 from Sheffield Hallam University here in the UK before proceeding into industry. She actively participates in the Science Society, presenting work and giving talks in over 25 conferences and workshops. Next, we will have Dr. Nina Baule will be taking us through how research organisations such as Fraunhofer drives innovation through applied research, collaborating with industry and academia. Nina earned her PhD in material science and engineering from the University of Dresden in collaboration with Fraunhofer in 2024. She mainly focuses on optimizing thin film materials synthesized via PVD to meet the demands of advanced applications. And then to finish the presentations, we will have Liz Josephson. Liz is the Vice President of Commercial Operations for Intellivision and the current President of the Society of Vacuum Coaters. And Liz has a BS in ceramic engineering from Alfred University and years of experience within the vacuum web coating industry. So she is a great person to be taking us through and giving us an insight into the roll-to-roll world. So as mentioned before, we will finish with the Q&A. So please put any questions into the Q&A box, and once all the talks have been delivered, we can get into the discussions. So I am very much looking forward to the presentations. These women are going to be showing us a little bit about their contributions into the thin film and vacuum coating industry, and how women are increasingly making their mark and excelling within their careers. So please, Lara, if you would like to start us off, then I'll pass over to you. Thank you.
Thank you, Trish. I will. Can you see my screen?
Not yet.
Sorry. Yep. Okay,
yeah,
so
thank you.
Yeah, thank you. So yeah, I will just take you through a bit of Gencoa, that's where I work, a bit of the basics of PVD, my journey from R&D, and how I moved into the technical sales role. So Gencoa was founded in 1995. You can see here on the right how is the company looking right now. We have a big floor area, not a big because we are a small company, but we have an area of manufacturing, R&D. So we are quite compact. We are like 38 people, and it was founded in 1995 by Dermot. Basically, we have been 3 decades producing products and technology for PVD. More specific, most of them are focusing on sputtering, but there is other products focusing on other vacuum applications. So a bit of Gencoa. So we have been applying vacuum plasma for a wide field of applications. I'm going to talk a bit more about the applications later. So we have been doing plasma magnetic field modeling in 2D and 3D. We have been making a sputtering plasma-based source and development. We have also been using plasma spectrometry to analyze vacuum processes. We can implement fast feedback control for unstable reactive patterning processes. So you can see on some of the images and on the nice video how we have like a broad field of application for different products. So I'm going to focus on sputtering into the physical vapor deposition because it's mainly what we do sources for. So in here you can see how is this a vacuum chamber. So this vacuum chamber is pumped. So it is reaching levels of -5, -6 um, pressure levels normally. Then this is the magnetron. So normally you will connect a negative voltage to it. And as a standard sputtering, that you will not have any magnets on the back. But what we are special here is to add some magnetic pack to the magnetron behind the target. That is the material that you're going to coat with. And with that magnet that contains in the magnetic field electrons that are going to be created, this allows you to lower down the power needed to create a plasma to maintain it. So these electrons, these ionized gas, this plasma that is created is going to ionize an inert gas that in most of the cases is just argon. So this gas is not going to react with at all with the target material. What it's going to do is going to sputter, so it's going to have an impact on the target, and that is going to release some of the material from the target, that it could be many different materials, and that is going to get deposited onto a substrate. And that's what we call normally metallic deposition. And when you introduce a reactive gas, in this case I have put oxygen, but it could be other kind of gases like nitrogen, this gas is going to react with the material that is coming from the target, that is going to form a different type of layer that in this case could be an oxide deposition. And then after that, all these gases are continuously pumping down, so you maintain the level and the cleanness of the vacuum. And this is more or less overall how sputtering works. So what we focus in is to create these devices between others, but mainly originally these devices that it can be of many sources. You can have different powers as different type of power applied to it, like Anna is going to tell us later. And you can also have so many deposition systems. So I just put in some examples here of ones that I know well. So we can have big post coaters, so where you can have different substrates that are being coated all at the same time. Normally are more like 3D or 2D, very small substrate that are put all together. And in this case, normally is so many different technology that you can use in this one, but normally, for example, a rectangular magnetron is one of the typical products that could be used because it has a larger uniform area, so you can coat different bigger substrates. Then you can have a small bore coater like this one on the right. So normally for this type of small bore coater, the circular magnetrons are something that are mostly used. It depends on the substrate geometry. For roll to roll, like Liz is going to tell us later. So for example, one of the big products used for it is ion source. This is kind of like the opposite to a magnetron. What we do is we use ions to impact onto the substrate and clean it for pre-treatment or post-treatment of the webs that are going to go through it. And inline system, this is to maximize throughput. So you put the substrate at the beginning, and that goes in a inline system, all continuously coating, pre-treating, killing, and then it goes out, so you have a continuous production. And in this case, for example, some sources that can be used are the rotatables. The target is rotating around, so what you maximize is target use, and you extend the target life. So just to have an idea of how STEM can be our products and the PVD world, and that makes it as interesting, is, for example, this one, the full phase erosion, where the magnets are rotating behind the target, so you have this type of erosion. Then you have BT flex, so we can go so far into creating different magnetic paths to adjust for different uniformity in a single magnetron. Then we could have any other different magnetic options, like for example this one, that you can rotate and convert one magnetic from being unbalanced to more balanced during the deposition. High yield for precious materials. As you can see here, you can use much more of the material. And we have in our case another type of products that are most for vacuum applications. So in this case, it's used for reactive sputtering control, but for example, optics, even if mainly right now is also used for sputtering and vacuum for PVD applications. It has like a wider range of market that as soon as it is vacuum implying, most of them it can be used to as a gas analyzer, but we also are creating a plasma between it. So it's everything related to vacuum and plasma. So in the applications, I'm not going to go through all of them because I could be here days, but we have, for example, decorative. As all of you may know, in your phone, you have a lot of different coatings that are coming from sputtering, but we have some decorative more functional, like yearly zips you have in the phone. You have harness and wear, for example, for DLC coatings to avoid damaging and scratching of the surfaces. You have tribological for hard tools. You have, for example, nice applications like for art, like the Jeff Koons, the balloon dogs. We have also antimicrobial for high touch surfaces. We have also for energy efficiency, like the electrochemical coatings that you may have seen in planes. For energy conversion, like all the solar stacks that can be created, the packaging, like the internal of the Tetra packs, optics, transportation, like the glasses of the windows and the screens of the planes, and electronics, like for the semiconductor industry and all the chips and things that you have inside your laptops and your phones. So a bit of my journey. So the beginning of it was in research and development. So I arrived in Liverpool in 2020 on an Erasmus internship. So as I was studying a master in biomedical engineer, I had to do my thesis. So I decided to come to Gencoa. They offered me a position, and I came to do these biomedical applications coatings, more focused in the high touch surface. So I was doing basically from the beginning all the coating to analysis to all the study technical papers, all related to that, and the antimicrobial test to test in-house the coatings. But at the same time, as I studied telecommunication engineering, I was also involved in the project of development of an oxygen sensor that is called backgas. So I was developing and designing the electronics and the firmware. So two completely different worlds. For me, mostly I didn't have any physics background, just the physics that I was studying in the degree, but it was not related directly to plasma. I didn't know what it was a plasma when I arrived. So that was a completely different world for me. And at the same time, I was doing two different completely projects. So the backgas is something that we use for vacuum analysis for oxygen, but it's not really related to vacuum what I was doing. So as you can imagine, it was quite far from what I was really studying at the moment or anything that I have learned before. So it was quite a shock. And at the same time, it was in another country, not my first language. So it was a big change. And also it was during COVID time, so you can imagine. And then from 2020 to last year in July, I have been working R&D, so at the same time I started to be involved in many different projects for government grants. So we have some government grants that we have been applying for developing some new technologies with collaboration for different companies, but also for some customer applications. So some of the customers can have some of the lab developed coatings and they want to industrialize it. So we are like in the middle there, so we can be developing some of the coatings here in like a bit bigger machines, and then we can also advise into how to create an industrial production for it. So we have so many coating systems. So I think it's 9 of them. They have different magnetrons, different applications, different geometries. We can do 2D, 3D kind of inline system, but a small one. We have a big one like this one that you saw on the left with a 1.5 meters. So I was, as you can imagine, every day learning a lot of many things. But it was so interesting, and obviously I really learned about about PVD, and everything is impossible because this is like a lifetime learning. But I also learned about the R&D philosophy behind it. So we have a lot of characterization system also. We could have more, but for that we use universities. We get help from university and research centers to help us with that. But we have few of them here. So many of them I didn't know anything at all about it. So it was also a learning of how to measure light transmission, reflection, all the antimicrobial coatings, the SEM. So it was quite a broad spectrum of things that I had to learn. And then last July, actually, when I was in SVC 2024, I was one night sleeping after a whole day of conference, and I decided that I wanted to give it a try to the technical sales, because I really enjoy talking with the people in SVC. They teach me a lot of things that I have never been learning things for one thing or the other. You learn a lot from customers, how are the necessities, what do they want, you learn how to listen to them and how to answer the questions. That is different than being R&D. So I decided to go for it. It was good because with all the technical background I acquired for 4 years in R&D, I had many things that I would not have had if I would have changed directly to another company. So it was fantastic. I obviously like Gencoa a lot, so that's what I decided also to try it internally. Obviously, my deposits are my best friend right now. Everything that I have to ask or have in mind goes into a deposit. I know it's not some too much sustainable option, but they save my life right now. I have obviously a lot of questions still, because even if I have some of the basic and important technical knowledge from R&D, it's a lot of questions now into sales, into design, to the intrinsics of the products, applications. You have to understand what the customer wants. You have to know how to ask the questions properly so they can understand you. It's a different countries, different languages, different way and cultures and applications. So it's quite interesting, but obviously I am enjoying a lot and I am learning still every day. Obviously, thank you to SVC, that apart from letting us create the Women SVC committee, that has brought me also a lot of confidence. It was also where I found what I wanted to do. So that is all. Thank you very much. I go through Anna now.
Yes, thank you, Lara.
Yeah.
I will now take over the screen. Okay, I hope you can see it. And now, in my presentation, I want to go through my history with HIPIMS Technology. So I will start with the where I have started, and then I will give some explanation why I love HIPIMS, how I feel happy with it, and then what I do with my job actually. So background to myself, I did 2 master. One was theoretical in Szczecin in Poland, physics, when I was investigating some carbon structures, and then also I did some more application physics at University of Rostock. And after that, I wanted to go more into the nanotechnology field about some new materials. And I was lucky to be accepted at Sheffield Hallam University for a PhD program, where I get started my history with HIPIMS. It was really a nice time where I learned a lot about the PVD, about the HIPIMS and all the application from the PVD point of view. Once I successfully finished it, I looked for the work somewhere close to my home. So I moved back to Poland and I started working with some glass coater and hard coatings. And then in 2017, I moved to the Trumpfhuttinger because it gave me a lot of option in developing myself and in researching with the HIPIMS technology. So I could go more and more in this. Trumpfhuttinger is a family-owned business. Generally, Trumpf is a big company with a lot of the branches. I'm in the plasma surface processing, and then it have a lot of the units. I'm located in Warsaw, in Poland, and I'm located within the R&D technology. In the R&D, we are having the plasma application group that was started in 2018. And the interesting thing that we have quite a bit of women in here. So we have 3. So and within the 9 people group. So I think for the statistic, it's quite nice. And in Poland, because it's divided by also different location, and in Poland, most of the people sitting in the office, it's women. So I think it's quite nice to show here that in Trump we look also about the quality of the people, and also we don't look that only men are going into technology. So we have quite a lot of girls in here that I really like. And now let's go to the journey of the HIPIMS. So I will give only the basic information, because with the HIPIMS I can talk for hours and hours, and I hope that I will not take too much time here. So when we think about the magnetron sputtering, typically there will be a DC discharge when you deliver power over time with the constant matter. And sometimes there will be also pulse DC. And you will operate in about kilowatts range. And if you want to go to denser coating, harder coating, you want to go increase the power. However, systems have limits, so you need a very good cooling system. Also, the power supply have very big limitation about the power that they can deliver, and because of that, there are limitations with the maximum power. But with the HIPIMS, you can go with the very short, very intensive peaks that it will go to megawatts, and then it will provide you very high ionized flux of the sputter material. And because it will be only 30% maximum of the duty cycle, so it will give a lot of the energy within a very short time, and then it will give time to cool down for the system and power supply to charge up. Again, delivering pulses, and it will be high, like high power within, so high flux. And what it will happen? So when you have very high energetic plasma, you have a very good plasma surface interaction. So you have this accelerated ions that will arrive to the substrate, and by heating one another, they can densify the structure. So more ionized plasma, more plasma current you have inside, the better structure you have, and you can go into better structure, more dense, less voids in between, and thus the mechanical properties of the coatings will be much better. And that is very good for a lot of the purposes, and you can have a very good smooth surface. You don't have so much macro particles. You can improve also the adhesion, and you can get very good control over the stoichiometry of the process. So just very quickly comparing with the DC, within DC, you have very limited power, that it's only at the low energy level. And that will, you can see that it's mainly dominated by gas, so by the argon ions and argon neutrals, and also by the gas, if you have reactive gas like molecule and some dissociated nitrogen, that will lead to the very columnar structure, and you can see some voids in between the system. In case of HIPIMS, the energy it's deliver on the also higher levels, so you can have both low and high energy, and this will lead to the plasma that have higher ionization level of argon. But what is most important, you will have much more percentage of the chromium, and also you have much more dissociated gases, like reactive gases, which you can control the stoichiometry, and that will result in the very dense, very hard coating. Hard coatings and dense you can also get with the cathodic arc deposition. However, here are the problem that cathodic arc is a bit different technique, where you deliver a lot of the power within one spot, and there are some effects where you have melting on the target, and you create a lot of the droplets, and then these droplets will solidify on the surface, leading to some microparticles, which can, for example, fall off and have lack of the corrosion resistant, and also lead to the very rough surface. With the HIPIMS, you can obtain very good smoothness, good density of the coating, and very well properties of the coating. And here is some research when it's comparing the HIPIMS and cathodic arc, and the mechanical and corrosion properties was much better. So here is the corrosion, and A, it's the bare substrate, B, it's the cathodic arc, and C, it's the HIPIMS. Also in the imprint, we can see there is much less damage. And from the scratch test, we can see that the load is much better and the roughness is much lower of the substrate. So that's just one of the example. And then the application, it's a lot of the application that it's limited here by the time, but main was the cutting tools and also some anti-corrosive properties of the coatings. Now, quite often we can see application for microelectronics and some micro tools, solid lubricants, anti-reflective and anti-scratch. And here for the anti-reflective and anti-scratch, I want to show you some of the results made at Sheffield Hallam University, where we investigated silicon oxide film, and the hardness was increased compared to the standard standard technique. And we investigated influence of the different parameters like reverse and reverse delay on the transmission. So not only you can increase the hardness, but you also can trigger some transmission optical properties in order to get very good protective top layer. And however, there are some downsides of the HIPIMS because when you have standard process, any process, there is a lot of the parameters that you have to take into account. So the properties of how you grow the coatings will depend on the gas properties of the what substrate you have, on the material source, what target type, what target material, also how much energy within the plasma you have, and also the power supply, how you will run it, which kind of the power supply, which kind of the discharge. When it comes to HIPIMS, there are quite a bit of other things that you have to think of. So for example, there is big influence from magnetic fields that will lead to self-sputtering. And then there is within the reactive sputtering, you have to be a bit more careful than in case of DC, because as I showed, there is more dissociated. So you have to know what you're doing. You can control very well, but you need to take into account that you have much more reactive processes. There is on the market plenty of different modes, different shapes, and then for different application, you need to use some other of it. Sometimes you need reverse, sometimes you need to dual magneton sputtering, and there are some kind of the multi-shapes, and this is a lot to take into account. And it's part of my job to support with this technology. There is a lot of investigation, both from universities and power supply manufacturer, because so many topics is there still to investigate. Some of them are already known, and then there is a lot of dig in. That's why it's so excited, because it's still new, it's mature technology, it's in industry, but there is so much more to dig in, to investigate. And then what do I do in my work? So my position is vacuum process specialist. So my first task is in-house and on-site customer support. So there will be a lot of the customer training, because customer needs to know how to use this technique, how to change from, for example, DC sputtering into the HIPIMS. I support product development, and I do some tests in the lab, and also this will lead to the chamber maintenance, because there is, if you work a lot with the chamber, you need to make sure it will be working. On the other hand, there is a part of the R&D where there are internal and cooperation research, where need to do some scientific papers looking for a possibility for more cooperation, and there are some project managers also tasks. And then the most fun part, it's knowledge exchange and scientific marketing, when with the information that I will get, I attend some conference, would share information, I can do networking, also doing some marketing writing, and also in order to get more knowledge, I will also attend some trainings and workshop. And from in-house test, we have a different chamber in the plasma group, where we can do different kind of the tests. We can do plasma test in the chambers, like a small chamber for batch system. Also, we have here we deposit samples, then the samples we can test. However, most of the investigation we do with the plasma, with the optical emission spectroscopy, and with the homemade plasma current probe, because this will give us very fast indication if we look going with this process in the right direction, if we increase the energy, if we increase the quality of the plasma, and then we can deposit some coatings and do some simple tests, or do cooperation and send samples for the investigation. And another, excuse me, big part of the my work is traveling both to the customer site and conferences. So here you can see me at the SVC conference, where there is a big exhibition when I can network with a lot of the customer. They can have some question to me and come to and work. Also giving some talks at the conference, and also doing some tests with different partners. And I really like travel, and with my HIPIMS history, I've been in many places. So the blue dots is how I travel with the HIPIMS related topics, and the green one is with my private travel. So I really like traveling, and this job gives me a lot of possibilities. You can see that I still need to feel some confidence, but there I try to be a lot everywhere. And then I think that's all. I cover all the topics. So to summarize, I really have a big passion for the HIPIMS technology, and I really love working with developing application and HIPIMS itself. There is still much to discover with the HIPIMS, and then Trumpf give me opportunity to do that. And if you have any question, you can send me email or call me. And now I have some question for you. How many plasma cuts have you seen? If you counted 7, you are right. And with that, I will finish my talk, and thank you.
All right, then I think I can take over now. Thank you, Anna. I hope you can all see my screen. Yeah, so now we heard a lot about Gencoa and Trumpf in the sense of Anna and Lara, and they develop technologies that are very suitable for the PVD industry. And I'm Nina, and I am working actually at Fraunhofer USA, where we do a lot of applied research using all of these tools. So Fraunhofer is really a global network where, let me just get my laser pointer, where Fraunhofer originated in Germany, where at this point there are about 76 institutes just alone in Germany, focusing on very different technology fields. But over the past decades, there have been a lot of Fraunhofer affiliates all over the world, and one of them is Fraunhofer USA, where I work, and where we get to later again. So the overall idea of Fraunhofer is really to bridge the gap between the basic research done usually in academia and industry. So if you work at Fraunhofer, you're really in this field where you do applied research and go up to potentially scale-ups where you help your customers to scale up their technology that you might have developed on the laboratory scale. So our funding mechanism is also is a big variety of government funding as well as industrial funding. So on one hand, we do a lot of public research where we apply for federal funding or state funding, usually in cooperation with a university as well as national laboratories, for example. And this public research is really often supported by internal research activities that we do. So these could be on a Fraunhofer USA level, but also on a global level, where we specifically partner a lot with German Fraunhofer institutes to drive certain competence areas forward. Then on the other hand, we also have industry customers where we do R&D work for them because they might not have the capacities at their own facilities to do this work. And that shows you very well kind of what I, on a daily basis, who I interact with. So I do a lot of interactions with MSU or in general professors, but also national laboratories. And then on the other hand, I have my industry customers that I interact with. So coming down more into Fraunhofer USA, Fraunhofer USA is a non-profit organization here in the US. And there are basically three main centers. One is in Maryland, where we focus on software development and artificial intelligence. Then there's one in Boston, where we focus on automation. And then there's the one in Michigan, that's where I'm located. And that one is the Fraunhofer USA Center Midwest. And we have basically two divisions. The one division is the division for coatings and diamond technologies in East Lansing, which is directly located on Michigan State University campus. And then we have another division in Plymouth, which is about an hour away from here, more towards Detroit, where we don't use a lot of vacuum technologies, but we also we focus on laser applications. So from these two locations, these competence areas really arise. So we have at our center, we focus a lot on diamond technologies, where we use chemical vapor deposition mainly to grow single crystalline as well as polycrystalline diamond materials. So these are all synthetic diamond materials, and they're not used for jewelry. No, in our case, we use them for power electronic devices or thermal management, and a big focus is also on electrochemical sensing. Then at laser applications here on the right, as I said, we don't really use a lot of vacuum technology here, but one interesting part that kind of overlaps sometimes with our field is the laser cladding, where you can really create relatively thick films. And then the coating technologies, that's where I'm part of. We develop, traditionally we developed a lot of wear coatings, so very hard coatings such as diamond-like carbon and aluminum titanium nitride for wear applications, for friction applications. But more and more, we really develop also these processes for energy storage, biomedical applications. And in the coatings group, we mainly focus on physical vapor deposition, and we're talking about thin films of a few nanometers up to several microns in thickness. Yeah, so my journey at Fraunhofer started in 2016, actually in Dresden in Germany. After I got my master's degree in material science and engineering in 2015, I started a graduate research assistantship there at the Institute for Material and Beam Technology. It was already the outlook of going also to the US in Michigan to continue my internship there for 6 months. And after I finished my internship, I decided to stay on as a full-time project engineer in 2017. And yeah, I started working as a full-time project engineer, basically running systems, developing thin film coatings. And I decided then in 2020 that I would also like to get my PhD, which I then did in collaboration with the Technical University in Dresden and Fraunhofer USA. So basically doing all my research at Fraunhofer USA and then getting my degree from the Technical University in Dresden. So in 2024, I got my PhD in material science and engineering, and I became a research scientist at Fraunhofer USA, with the goal of growing more into a principal investigator role and building my own group. So here you see a picture of our PVD laboratory at Fraunhofer. We have a variety of technologies, but I would say we focus on arc technologies, so pulse cathodic arc, also laser arc, which is a special proprietary technology developed by Fraunhofer. And then we also have several systems for magnetron sputtering. Here we have target sizes from 2 inches to 400 millimeters. So really trying to get this prototype sizes more working for our customers. And in this laboratory, we have a variety of people. So there are scientists, technicians, engineers, but also students that work here. So it's a variety of people, and I really like that about this job. For students, we actually have international students where they come on a visa program to the US or have the opportunity to do that for up to 12 months. And then we also have local students, in our case specifically, mostly from Michigan State University, that work with us usually on an hourly basis. So the overall idea of what we do, or I do on a daily basis, is really developing thin film materials using PVD technologies. And how I usually do that is I have a process, for example, magnetron sputtering, as you can, which is shown here schematically. And I will change my process parameters and then see how the change in the process parameters correlates with my material properties and the material performance. So this is basically a back and forth until I really have the function that I want from my thin film material that is for a specific application. So the properties depend very strongly on the application. So one example here is nitrogen incorporated tetrahedral carbon materials. This is actually the work that I did for my PhD. So I wanted to use this amorphous carbon material, also known, people probably know it more under the name diamond-like carbon. And I wanted to go away from those typical wear applications for this material and use it for electrochemical applications. And really the motivation behind that is that amorphous carbon has very much diamond-like electrochemical properties, not just mechanical properties. That means that we have a relatively low background current over a wide working potential window, which you can see over here. And that means for electrochemical applications that you can analyze a variety of analytes at very low detection limits. So compared to, for example, boron-doped diamond, though, which is synthesized at really high temperatures, the amorphous carbon can be synthesized at basically room temperature, and it is roll-to-roll compatible. So the overall scale-up and then economical advantages are very clear. And we can potentially deposit it directly on polymer substrates. So for my work, I basically focused on the material properties. An example is here on top, where I looked very specifically at the electrical properties of these materials and with some kind of novel technique, and then used my knowledge that I gained from there to develop the actual application. So here on the bottom, you see a 4-inch wafer with so-called 3-in-1 electrodes that are typically used in environmental sensing or medical sensing to really push this electrochemical application or sensor forward. Another one was to develop an optically transparent electrode, which you see over here, which can be used for spectroelectrochemical analysis. Another example for magnetron sputtering now, so what I showed you before was an ARC technology, is that we investigate a lot the single beam ion source enhanced magnetron sputtering, where in collaboration with one of our MSU professors who develops these ion sources, we try to enhance our magnetron sputtering, the material properties at the end with this enhanced ion beam. And the idea is really to densify the film and have another basic knob that you can turn to change your material properties. So here you see an example of indium tin oxide, where you can clearly see that the crystalline properties of the material change with the ion source voltage. So these are just a few examples I wanted to show you. There are far more that we work on, but yeah, that was it from my side. Thank you all so much for your attention. If you have any questions, reach out to the women at the svc.org or just directly to me. And yeah, now I'm going to give the floor to Liz, who's going to talk about web coding, vacuum web coding.
Thank you. Okay, well, that was a great introduction by everybody for what I'm going to speak about. So we heard about source of technology, we heard about power supply technology, and also some applications in thin film technology. And SVC covers a really wide range of applications and industries, all related around vacuum technology. So I'm going to talk about one very specific part of that, just a very small part of the SVC, and focus on what you can do with roll-to-roll technology. So roll-to-roll technology has a lot of benefits. It has some limitations, but it does have a lot of benefits. And one of the biggest is that it's a very versatile and scalable technology. So you can develop a product and then transition to roll-to-roll. So really, as long as you can get a material in a roll format, a substrate that you want to use, and you can, theoretically, you can do vacuum deposition on it. So as long as you have the functional material that you want to put on a substrate, either optically or mechanically, or other properties that you're looking for, barrier properties, if you can put it onto a roll-to-roll, a flexible substrate, you can theoretically use vacuum roll coating technology. So this is the really cool thing about this technology, is that using the same type of systems, you can touch so many different applications. So I know Nina talked a little bit about that, but just in roll-to-roll, this is not talking about hard coatings, this is not talking about glass or anything else, or semiconductor, this is just roll-to-roll technology. So we cover a wide range of applications: electronics, energy with photovoltaics, batteries, solar control, window films, you have sensors, you have biomedical sensors, diagnostic sensors, and I'll show you some examples of that. And there is also a whole other range of applications. So aerospace, barrier, optical coatings, holograms, I'll talk a little bit about that, security and antitrust, and other specialty applications. And all of these have a long list of requirements, but the key to what I'm talking about, and this is focused on, is the flexibility. And flexibility can be looked at two different ways for roll-to-roll. One is that you need a flexible substrate. It has to be able to be wound onto a core and put into a vacuum chamber and unwound and then rewound. But flexibility also means we can have a variety of different sources. We can do a lot of different things to the substrate as well to have it perform to the final needs of the customer. So there's a lot of things that go into a roll-to-roll technology, into a roll-to-roll product. And I'm just going to touch on these very, very high level. So The most common roll-to-roll application is in the food packaging industry, where there are and all of these technologies, I'll say, are global. So especially food packaging, and food packaging is the largest market by volume, and there's probably the most number of roll-to-roll vacuum coating machines installed for this technology. So you're running at very high speeds. You're running it up to 18 meters per second. You're putting down a very simple aluminum layer, but it's providing a barrier, and the barrier allows for just for in snack foods, it adds for either a light barrier or water barrier or an oxygen barrier. So it's really applying 3 different types of benefits to the product, and that's the biggest volume of materials are used for that. Then you have other applications, which I touched on: energy related, flexible electronics, medical devices. Most cell phones have a flexible transparent conductor in them that is, as we go to lighter and lighter weight cell phones. And then you also have a lot of specialty other applications. So just a very general overview of how roll-to-roll works is everything has to be put in a chamber and pumped down. So you need, as I said before, you need your substrate in a roll format. You put it into a machine. You typically unwind it. Typically, it's coated on, your coating is done on a drum so that you can handle and work towards handling heat related issues or cooling related issues, and then you rewind it. And all of that is done inside the vacuum chamber. So there are different ways to do that. You can do some applications. Very few have done it in free span, where there is no drum associated with it, so that they don't have as much control over the thermal management of the substrate. But typically there is some sort of drum that is supporting your web. So we can do a ton of different materials. So we've done the nice thing about this is you can deposit a lot of different materials, and we also have a lot of we've run a lot of different substrate materials, and I'll talk a little bit more about that in a minute. So this just kind of gives you an idea of how broad vacuum roll coating deposition is. So when you look at packaging and window films and holograms, gift wrap, things like that, more commercially available products, they typically start about 2 meter wide machines, and they go up to 4.5 meters wide. So that's a pretty significant amount of material that you're moving through at 18 meters per second. So that's, food packaging, things like that. Then you get into a little more specialized products, I'll say, which are more like solar control and window film, and they're about 1 to 2 meter wide machines. And then what Intelivation focuses on is systems typically that are around 1.5 to 2 meters, although we do the 2 meter machines as well, but these are more fixed, I'll say fixed display applications, optical coatings, multi-layer coatings. And then there is also a market for smaller, less than 1/2 meter machines. So you can look at mobile electronics there, you can look at medical devices, you can look at wearable devices. And don't forget that when you're looking at some of these applications, these devices can be very, very small, 1 to 2 centimeters, or even smaller than that in millimeters. So it really depends on what your end product needs to be as to where you fit into this array of different sizes of systems. And there's also pros and cons for each for where you look at where your application falls. So when you look at these high speed machines, you have very high speeds, but you give up some other things in terms of multi-layers or functional layers, different functional layers that you can deposit in these systems. But throughput is very high on these wide systems. So you need to understand what your end product is and what sourcing you need, as well as what kind of line speeds to match up with what kind of system would be perfect for your roll coating needs. So this just shows you a couple of different systems, and when you look at the overall architecture of a vacuum roll coating system, there's a lot of things that come into play. Web handling. So we're going to talk about substrates and how that can be impacted. So surface substrates and cooling. So as I talked about cooling drums before, there's pre-treatment. There's different deposition technologies that, like Lara mentioned. There's also different power supplies, as Anna mentioned. And then also it's very, very important, and because most of our systems are going into industrial applications, is your in situ monitoring. And I'll just touch on that for a moment too. So when you think about this and look at this for high volume food packaging, this is just an example of two different types of high volume substrates that are made. So one is a polyethylene here and one's a polyester. These are made in very high volumes. And then you can look at an OPP line, which is biaxially oriented polypropylene. And those can be up to 8 meters to 10 meters and I think 12-meter wide lines now. So that's a huge volume of material that now you need to also, and for a large part of that needs to be vacuum coated. So that's where you look at these systems that are 2+ up to 4 meters wide, running at 18 meters per second. So when we talk about different kinds of applications, so there's a wide range of materials that can be run. So typically not in those big machines, you don't see the flexibility there, but as you get into the smaller sized machines that are more focused, I'll say, on sputtering technology particularly, you can look at you can look at different polymers, you can look at metals, as long as they can be rolled. Textiles, ceramic, rolled ceramics, flexible glass. We've done a lot of work on flexible glass. It also depends on what your temperature requirements are, your optical requirements. Do you need a transparent substrate or can you use something else? And also, you also need to understand your sourcing of this. Like, can you get all of these materials in something that can be rolled and then put into a vacuum chamber? So all of those are important to keep in mind when you're thinking about how to transition to a flexible type material. So there's drivers that everyone is looking at when you're looking at thinner, lightweight devices that are cheaper, things like that. Textiles, all of these have an impact. They have an impact on your vacuum as well as an impact on terms of how you handle them. So this is just a very quick overview. Pre-treatment's a big requirement in a lot of roll-to-roll applications, and it's used primarily for three different reasons, either for adhesion, for degassing of a substrate. So if you have a substrate with a high volume of material, or you can use degassing. You can also use it for cleaning the substrate. So depending on the quality of substrates that you're coming in, often you have to do some sort of management prior to when you want to deposit something on them. So now I'm just going to, again, talk very roughly. And again, remember, I'm only talking about roll to roll. So a lot of these are applicable to, I'd say, rigid surfaces or glass surfaces or silicon surfaces or things like that are in other aspects of vacuum coating. But specifically in roll to roll coating, there's a couple of different, probably predominantly, I'd say predominant technologies that are used, and evaporation is one of them. So thermal evaporation, and that's what's used in these really high speed machines. You're looking at high deposition rates, you're looking at high line speeds, you're putting down single materials. Then you have also electron beam evaporation that can do very similar things, but you can evaporate a lot more materials. You can pretty much evaporate anything that you can put into a vacuum chamber at a very high energy. So this just shows you what the evaporation source looks like. These are intermetallic ceramic boats, and actually I forgot to weave into how I got into this. This is how I got involved in the vacuum industry, as I'm a ceramic engineer, and I originally started working with a company that provided the intermetallic boats for deposition, and that's how I ended up in this industry, and then working with machine manufacturers who use these. So you can use intermetallic boats. These are what's used for food packaging. So you're feeding in feeding in wire, an aluminum wire, and evaporating at a very high speeds. And similarly, electron beam technology is very similar as well, where you have a beam, a very high-powered beam, and it's evaporating something, material, either an oxide, a mixed oxides, or a metal at very high speeds again. And here, what this is used for, one of the biggest applications this is used for is for transparent berries. So when you look at clear berries in food packaging or in other flexible packaging applications, they're typically being made using e-beam technology. And it also is used a lot for security applications. So holograms. So if you think about currencies, when you have different different index of refraction layers, you can do that going back and forth using e-beam technology. There's also induction heating and evaporation that's not as used as much anymore. That's kind of where technology started, and then it transitioned to resistive. And this just gives you an idea of kind of the idea of how a roll coater works. So again, you have a chamber, you have a vacuum chamber, you have an area where you load a roll, you unwind it, pass it over a coating drum, and then rewind it after something's been deposited on it, whether it be deposited by evaporation or sputtering or some other deposition source. This is typically how most vacuum chambers, roll coating chambers, are laid out. So there's typically different levels of vacuum in your winding zone as well as in your compared to your deposition zone. So the cool thing about this is an older picture, is this also showed some technology where for capacitor, specifically for capacitor manufacturing, where there's a band masking inside the chamber. So you can actually have band masking that runs in your deposition zone. And this is typically for very simple band masking, where you have just lines down your on your metallized surface. And it's a very simple, but it's been used in the battery industry for decades. You can also now, a lot of technologies incorporate what they call oil masking for in thermal evaporation, where you can pattern mask with oil, and based on the high speeds of this evaporation technology, the oil just evaporates during the dissipates during the evaporation process and leaves you with your patterned surface. So this is just another kind of example showing a different way for electron beam. And then we get to sputtering, which we've talked quite a bit about today, which is most of our core competency is in sputtering, although we do have used a lot of other things. And there's different types of sputtering. So obviously rotary magnetrons, planar magnetrons, we have magnetic target sputtering. Again, here talking about all the different sources, power supplies. And Anna talked about HIPIMS specifically. She touched on a little bit on comparing it to bipolar DC, and there are other DC, RF, and other source technologies. So the combination of what you want to deposit will also start driving you towards which type of sources that you're going to use and which type of power supplies. So here again, this is just a planar sputter magnetron, so you get lower deposition rates than evaporation, but you get really high quality, very uniform products, very repeatable products, and very tunable. So you can have a wide range of materials. You can also do reactive deposition. So here I'm showing some a dual rotary magnetron. So here that's used, a lot for oxides, reactive deposition. And being able to control the process very carefully is also very important. So I'm not going to go into much detail. You can also look at CVD, which is chemical vapor deposition. Most of what we've talked about today is PVD, physical vapor deposition. You can also look at plasma enhanced technology, or ALD. So there's quite a bit of other technologies that can be implemented into roll-to-roll technology. And I mentioned this earlier. One of the very important parts of it is obviously is process control and in situ monitoring. And this is where we've kind of been pushing the envelope recently on some of our technology regarding in situ monitoring. So opening up the wavelengths that we can monitor in situ. And there is a lot of different applications, and each application requires different types of monitoring. So here we also talk about reactive control. So when you're sputtering, your reactive process control, how you control it, if it's reactive with PEM, plasma emission monitoring, or volt modes, and allows you to have very consistent and high deposition rates and to monitor them in situ. And then I'll show you a little bit on, so when you talk about this, and this is a little bit busy of a slide, but it just kind of talks about when you talk about metal depositions. So either if you're evaporating or you're sputtering, you can measure transmission in line or sheet resistance to give you your in situ and closed loop controls in a conductive or a transparent conductive oxide system. You can look at, again, transmission, you can look at sheet resistance, you can look at these as single point, multi-point, cross-web scanning. So there's a lot that can be implemented into your roll-to-roll applications or to your product, right? In sputtering, there's also a huge range in terms of single wavelengths, multi-wavelength scanning, different spectral reflectance or transmissions, and the key here is if you can wrap this into a closed loop system for manufacturing your flexible product. And kind of towards this is kind of giving you an idea of why roll-to-roll is important. So as I mentioned up very early on, is at some point almost everything that is made in a vacuum roll-to-roll system becomes a discrete part. And when you make the decision for that to become discrete is important, and that helps you build your manufacturing costs and kind of where you want that to happen. So this is just an example of a biomedical device that was manufactured, that was done on flexible glass in a vacuum roll-to-roll system. This is also unique because we used some really cool laser technology as well to help modify the surface of the sputtered layers and change the morphology of them to help to work in these medical devices. But as you can see how small these devices are, you're looking at a million a day, but you're doing that in a single, in just a few rolls a day of sputtered material gives you millions of devices. And this is a concept of the same thing as how you could implement all of this into a full-scale production line for roll-to-roll technology. And implement that, and including laser patterning. So just in summary, I wanted to focus on a couple things. One is that high-end applications for sputtering and roll-to-roll applications, you can use a lot of different technologies. We didn't talk a lot. It's a very short time, but we can talk about multi-layers, multi-pass. We have customers who do coatings that are 100 material layers thick, and they're passing it back and forth hundreds of times, all in the same pump down. So they're very complex, multi-layer devices. And there's a lot of in-situ technology that can be used to help you maintain and ensure that you are doing this. And also precision deposition is also important too when you think about roll-to-roll technologies. So again, if you can move to a flexible substrate, it does become very, very cost effective to be able to do high volumes of materials when you're looking at putting different depositions down on them. And then I'll take off my Intelivation hat now, and I'll go and talk about, for there's a lot of new names I see in this webinar, which is very, very exciting. I'm thrilled to see so many new names and new people, but SVC, we are part of the Society of Vacuum Coaters, and we have a TechCon coming up in May. And one of the really cool things that we've implemented in SVC is that we allow anybody who's registered, has full registration. We give you access to our education classes. There's a plethora of education classes in any aspect of vacuum coating technology. And also the TechCon program is also a great source of getting access to new technology and seeing what is being done in the vacuum industry. So thank you very much. I'll turn it back to Patricia, our moderator.
Hello, thank you so much for those 4 incredible presentations. I have certainly learned a lot, and it was just fantastic to see the contributions that our 4 lovely presenters are making in their industry and within their own companies. I think it just goes to show how important gender diversity is in industry, and how when we work together, you can feel that innovation, as kind of touched upon in Nina's presentation. So yeah, I think they were all fantastic and very inspiring, and we have got a few questions here in the Q&A, so I will go down to the bottom, quite a few questions, which is great, and please keep adding to them if anything comes up on the back of this as well. So I think the first one will go back to our first speaker, Lara. So one of the questions is, could you tell me more about how the antimicrobial coatings are working? So I know that there's a vast number of different antimicrobial coatings, but maybe you can touch upon what you were working on.
Yeah, thank you, Tris. So the ones that we were working on is a lot of different methods of application, a lot of different methods of being antimicrobial, but in our case, they are copper-based coatings. So they work in light and dark conditions. So it is counting on that oxygen redox reaction that could happen with the atmosphere. So that will destroy, in our case, the antimicrobial or the microbe that we want to kill. Is different ones that we have been testing, and that will destroy and make inactive the activity of the microbes. So we have been testing them in some places like ticketing machine in train stations, but also mostly in hospitals. So it's for like high touch surfaces. So hospitals where you don't wash properly your hands, you cough in your hand, you touch, and then the next person, it has to be active quite fast. So you are not transferring microbes between people. And yeah, they are quite nice and they can be transparent or decorative depending on if it's for screens or for buttons. Yeah.
Thank you. And then we have another one. I think this is probably for you, Anna, and it's, can you explain the benefits of DC over RF sputtering, if any? So I know you're mainly on HIPIMS, but if you can answer this.
So if you compare DC and RF, I would say the biggest benefits from DC is the simplicity of using it. So it's the most simple technique, and also the deposition rate, which is much higher comparing with the RF. So, but from the other side, the RF can do work on the targets that DC will not work. So it will be very difficult to use DC in ceramic targets, but then you can support with RF. So there are two different totally techniques for different application. And depending what you want to do, can go either DC, either RF, and then it's usually the difference between the sputter rate and possibility of discharge at all. Okay.
Thank you. And Nina, you showed us the locations of all the Fraunhofer Institute. So do you get to work with your global colleagues? And if so, what's that like? The consortium between you, or can you touch on that?
Yeah, so we do do a lot of collaboration between Fraunhofer USA in general. So for example, I just started a project, internal project on using AI for physical vapor deposition. So that is then in collaboration with the software development one in Maryland. And then, yeah, overall, there's also other programs where we collaborate specifically with our German counterparts on a lot of projects. Yeah, that there is a variety of projects, but yeah, we just had this this call for funding opportunities where we can apply for funding like that too.
Great, yeah. And do you get to travel to different sites?
Yeah, I do. I mean, it's nice for me because especially when I collaborate with the Germans, I can go back to Germany where I grew up. Yeah. So that's nice. But I've been to Boston, I've been to Maryland, to their locations as well. Yeah.
It's good. It's always nice to get traveling. And then Liz, thank you very much for the in-depth view on roll-to-roll and web coating. I found it really, really informative. And we do have a question from one of the attendees asking, I think it might have been missed, but is the drum always chilled or usually chilled during the deposition?
No, it depends on the substrates that you're using. So you can have a chill drum or you can just have a coating drum. So it depends on what your substrates are, what your heat management needs to be, what you're depositing. So it's an option. So it doesn't always need to be chilled. Typically it is.
And do you think the advancement of the web coating is or the technology of web coating is continuing to advance? Because you touched upon kind of the large industries and sectors they're in, such as the manufacturing of packaging, but is there more growth for web coating?
Well, I think there is. I think there's growth for the applications. The technology, I mean, there's physics, right? So we're all in the world of vacuuming. There's only so much you can apply to physics, right? Or use physics for this. So there are some limitations, but we're doing a lot of work with different coatings and different depositions, as well as we broadening, like I mentioned about our in situ monitoring. But the applications themselves are endless, and that's kind of the cool part about this is that when I showed that first or second slide is that whole range of applications. So I have to say almost none of our customers are in the same industry, so that's really cool. So it is very, very broad, and every day we get calls about something completely new. So in that sense, I don't think we're limited.
Great, thank you. And then lost, they've jumped to the top. So actually sticking with you, Liz, someone's asking, how do you deal with vapor condensation inside your roll-to-roll line with e-beam processes?
Well, it's the same. Well, it's not the same because they all have different ways that the plasma is generated and where the plasma goes and how the plasma goes. But all of them have shielding that you have to keep clean, and that's part of your maintenance. So it depends on what technology you're using and how much and how frequent that is and how often you have to clean. But cleaning in a vacuum deposition system is part of anybody's maintenance.
Thank you. And we'll go back to Lara. So you were talking about coming over for the Erasmus internship. What was kind of the hardest challenge moving country, learning a new language, and what was your greatest excitement from it as well, making that decision to stay here permanently?
Well, all of them. I came here young, not speaking English as my first language, with just a degree. So what I mean is I didn't have any PhD. That most of my colleagues, when they have started working at Gencoa, they had a PhD. I didn't know anything about plasma. I don't know. This could feel stupid that but I am quite short. So, it's like I don't occupy so much space. And I am a woman, so it was kind of completely challenged in many cases. But I have always heard that if you think that you can do it, you can do it. So everything was, I mean, I had a lot of support. So when I came, it was also COVID time. So you can imagine it was all unsettling. I didn't know what I was doing and why I was here while the world was getting crazy. So, but I had a lot of support from all my colleagues and a lot of people here and just encouraged me to be myself, speak, and if I commit some errors, speak in English, that's all right. So yeah, that it was a challenge.
Good, good. We're very happy to have you here. And someone is asking, how do you feel as a woman in this male-dominated industry in your new role in sales? And have you ever encountered any negative situations being a woman?
So unfortunately, yes, they are not like, it's not something that you see clearly. It's not something that you actually, someone tells you in your face, oh, you are less because you're a woman. Obviously, they aren't going to be that clear. But I have had some situation like where you can feel that they have decided to prefer to talk or to address directly your male colleague than you, even if it's your job, what they are looking for, like, they are looking for to talk about something outside and they have addressed the male colleague directly. It could feel that it's a coincidence, but after many networking events where I have felt that everyone was knowing that if I was a technical side, they were going to talk to me. You see the difference when someone is not addressing to you the first, and they know that is your position. So, but anyway, you just have to, you have to understand that it's different generations, different cultures. It is not their fault, neither, it's something that happens. But that's why we have this committee. It's just to try to avoid that nothing like that happen anymore, just by, getting to know people that situation exists, even if we don't think it happens as many times, but sometimes it happens. So
yes,
the more women, the less they can do it. No, I'm just kidding.
No, I think you said it well, and that's kind of why we set up this committee, so that we have this kind of community where we can discuss and talk about the kind of experiences and things that we have encountered being not the majority within the industry, but it doesn't hold us back, as we have seen in the presentations today. All of these fantastic women are doing incredible things for their companies and for the industry, so it is fantastic. And touching on, obviously, Lara, you moved here to the UK from Spain, and someone is asking Nina, how is life in the US and do you miss home? Do you ever feel homesick?
Sure, I do feel homesick sometimes, especially when I haven't been in a while. When I just went, then I'm also always happy to go back. I think it's very exciting to feel home in two different countries. So I noticed that now. I feel very comfortable in Germany. I feel very comfortable in the US. And yeah, for me, it's more, I just find it exciting. I'm still learning every day something new. I appreciate language far more. I appreciate culture far more. I never thought about those things beforehand as much. So yeah.
Good, thank you. And then I'm not quite sure who this is directed to. It kind of covers power supplies, so possibly Anna or Liz. You can let me know who wants to jump in. But there is a question regarding power supplies in large area magnetron sputtering related to dual magnetron sputtering and medium frequency, and it's how to control the TIN dust during deposition in large area magnetron sputtering, and what precautions would you have to follow. So I guess Liz, maybe do you want to take this?
Oh, I was going to defer to Anna on that.
Oh, Anna, yeah.
Okay, so I can answer some of the questions. So definitely when you're going in titanium nitride, it's one of relatively simple deposition. However, you need to always think about stoichiometry of the coating. So in order to have this nice shiny golden color, you need to think about that it's a reactive process. So you need to control very well the gas consumption. And in order to have good coating, usually you need to have very good energy. So quite often this coating is deposited in the higher temperature. And if you cannot get a very high temperature, always you can use HIPIMS to enhance the energy. So that's also a very good way. But in the large area, definitely you need to think about gas distribution and the distances between the cathodes. If you're thinking about the dual magnetron sputtering, I think it's quite good because then you have this clearing effect of the target, so you will have less accumulation of the charge. And even better if you will have some kind of rotatory magnetrons that will also further increase the stability of the coatings. I hope those answers cover the question. If not, then you can ask more or reach me out on the email, then I can answer you more questions.
Thank you. And we have maybe a couple more questions. So someone has just asked a question for Liz. How do you apply the mask to create devices on web? Is it an inline process?
So I showed the picture of the capacitors. So in capacitor manufacturing, when you're just doing high speed evaporation, thermal evaporation, you can do it in situ. In situ. The work that I had showed at the end is currently done offline. There are concepts to do it inline, but right now, the process for how that's done, and it's a subtractive process. It's not using a mask, it's using a laser technology. So you're doing your patterning with a laser, not with a mask. So they are a little bit different. But both are options depending on what you're depositing and what you need, what your final product needs to be.
Thank you. And then we'll stick with you, Liz, as we wrap up. And could you kind of talk us a bit about your path to becoming president of the SVC, seeing that we are the women of SVC, and I think all of us kind of find you inspiring. It's kind of the leadership roles that I hope to one time go into. So yeah, if you could tell us a little bit about how you got there.
Well, thanks. That's a very humbling question. I'm not sure I ever aspired to be president of the SVC. And so I was very flattered, and that's probably how I ended up here. They played a bit on my ego, right? But I have to say, thinking about this and listening to all of your past and how you got involved in vacuum technology, I was introduced to vacuum technology very shortly, like a lot of you, right out of school, when I was a very young engineer, and started attending SVC conferences. the best path is really just participation. And as you guys see, I mean, you guys just, I'm so impressed with what you've done with the women's group in the SVC. It's the biggest committee within the SVC. It's one of the most a very active committee in the SVC. We have, I think, we've once said we probably have the largest voting power now within the SVC. But being involved is the key to it, right? Participating in being active in committees, helping with committees, helping with TechCon, attending things, there's so many opportunities at TechCon to be involved in things. We didn't even touch on the foundation, and Paula, thank you for the question. I appreciate that. The SVC there's another arm to it, which is the foundation, which is really focused on educating and making sure that we're bringing people into this industry and supporting them well. So it's really, participation is the biggest role I would say, to getting more involved with SVC. But that's true of anything, I think.
Yeah.
So
yeah, no, thank you so much. And yeah, just to remind anyone that might be new to SVC or hasn't attended any of the TechCons previously, it will be held in Nashville this year on starting I think the 19th of May is at the start of the conference and presentations, but there is the educational program before. I haven't got a calendar in front of me, but I think it's the 19th of May. And on the 19th of May, so the first day of the technical program, will be the Women in SVC in-person meeting. So if anyone is lucky enough to attend the TechCon this year, then please do attend the Women in SVC in-person meeting at 6 p.m. Am I right saying that, Lara?
Yes, I think. We will be there anyway.
Yes.
During the whole day, so.
Yeah, no, well, thank you so much to our fabulous speakers, and they were fantastic presentations. As I mentioned before, this has been recorded, so it will be available to watch back or show to any colleagues via the SVC YouTube account. So I just want to thank each and every one of our attendees for joining us today. It means a great deal to have the support for our very new but well attended a committee, as Liz was saying, and we're growing in numbers, and anyone that wants to be more involved within the committee, then please do get in touch. Follow us on LinkedIn, and yeah, we can introduce you. So thank you so much, and that is the end of our event.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, Patricia.
Bye.
Bye.
Bye.